Hello and welcome to Celestial Navigation Demystified. My name is Tim Brill, and I want to talk to you about some of the concepts that you probably should know before you start practicing celestial navigation. I learned this the hard way because I was practicing before I understood what I was trying to do. So this is born out of years and years of frustration and practice. But before we get into that, let me tell you a little bit about who I am. By profession, I'm a pilot, and like lots of pilots, I'm also a sailor. Probably because the physics, lift on wings, lift on sails, they're identical. As far as the sailing world, I do have a merchant mariner credential as a master with a sailing endorsement. I've sailed around the California coast, the Baja Peninsula. I think I've done the Baja Haha fun little thing about 3, 4 times. I don't remember now. Of course, Sea Cortez, Florida, the Caribbean, the French canals, which really wasn't sailing, and so far one circumnavigation, most of which was on my own, and that's where I got really bored and decided to learn about celestial navigation. To date, I've probably done a little bit more than 45,000 nautical miles. And yeah, that's what I've done sailing wise. Celestial navigation, tends to be kind of spooky to people primarily because, well, there's a lot of concepts that you don't use very often anymore. So you tend to get a little scared about it. But it is a lot of fun. So what I want to talk about in this video is start off talking about the terminology that you use when dealing with celestial navigation. There's some words that are a little bit awkward, and then we'll talk about the tools that you'll need to do it. And then we'll talk about the big picture, what you're really trying to do. We'll talk about noon sight for latitude, latitude using Polaris, and finally the 5 steps for a successful sight reduction using the Marc St. Hilaire altitude intercept method. And yes, that's the gentleman's name. And in my case, publication 229, which is nothing more than a calculator for solving spherical trigonometry problems. So we'll get into all that. At the end of the video, I'll give you my email. So if you have any questions, you're always welcome to email me. And I do have all my pages of notes in front of me here. And I'm more than happy to forward those copies to you. Again, you just give me your email and I'd be happy to do that. So let's talk about some of the terminology. Let's start off with something that we know. Latitude. Everybody's familiar with the equator. The equator, by definition, is 0 degrees latitude. Now, latitude and all these things we're going to be talking about are broken down into degrees, minutes, and seconds. There are 60 seconds to 1 minute, 60 minutes to 1 degree, and up to 360 degrees in a circle. I say up to because latitude, you're not going to get more than 90 degrees, and we'll explain why in a minute. The equator, as I said, by definition, is 0 degrees latitude. As you go north of the equator to the North Pole, you're in the northern hemisphere. As you go south of the equator to the South Pole, you're in the southern hemisphere. The northern hemisphere, North Pole, is 90 degrees north latitude. The South Pole, of course, 90 degrees south latitude. What's interesting about latitude, particularly interesting, is each degree of latitude corresponds to a real distance on the surface of planet Earth. Each degree of latitude is, in fact, 60 nautical miles. And since there are 60 minutes in a degree, each minute of latitude corresponds to 1 nautical mile. So if you ask yourself, well, how far is it from the equator to the North Pole? Well, the North Pole again is 90 degrees north latitude. So that's 90 degrees times 60 nautical miles per degree. That's 5,400 nautical miles. Um, it's a great way to determine distance. And it sets up a coordinate system. That's the north-south part of the coordinate system that you'll use on your charts and maps. If you looked at your globe, you'll find two other interesting latitudes that have names. One in the northern hemisphere called the Tropic of Cancer, one in the southern hemisphere called the Tropic of Capricorn. Each one of those is approximately 23.5 degrees north or south of the equator. Now, what's important about that? As the sun revolves around the earth, it doesn't stay right on the equator. It kind of meanders north and then south and north and south. The farthest north that the sun will go in what would be the northern hemisphere summer is about 23.5 degrees. And that is what is called the Tropic of Cancer. Conversely, the southmost the sun will move is 23.5 degrees south of the equator, Tropic of Capricorn. So those two special lines of latitude basically just denote how far north or how far south the sun will migrate during our rotation around it, our yearly rotation. So that's latitude. Longitude, or longitude if you're from Europe, will basically are lines that go from one pole to the other pole. They don't go around the earth. They're not parallel to each other. Incidentally, latitude lines are also known as parallels, but they'll go from the North Pole to the South Pole. The 0 degree longitude line happens to be an arbitrary line right now in Great Britain in the Greenwich Observatory. So basically it's called Greenwich time, the Greenwich Meridian, the prime meridian. That is 0 degrees longitude. Interesting that it's in England because 100 years earlier, France had the same idea. And if you go to Paris, you'll actually see their 0 degree longitude lines paved on the road there. But oh well, I guess the Brits had more military power, so they took it over. And now it's in the Royal Greenwich Observatory in Greenwich, England. That is 0 degrees longitude. Now, fortunately or unfortunately, depends how you look at it, the Brits decided that the sun will never set on the British Empire, so they broke longitude up into 180 degrees east of Greenwich and 180 degrees west of Greenwich. So you have east longitude and west longitude. It just makes the math, as we'll see here in a little bit more difficult, but otherwise it's not too bad. So, and the problem with longitude as well is that you can't measure an accurate distance just using longitude. The only place where 1 degree of longitude will equate to 60 nautical miles of distance on the surface of the Earth is the equator. As you go north of the equator or farther south of the equator towards the poles, those lines of longitude actually start to come together. And in fact, at the North Pole and South Pole, all the longitudinal lines meet. So the distance that you have between one line of longitude and the next line of longitude depends on, oddly enough, your latitude. If you're at the equator, it's 60 nautical miles. As you go farther north or farther south, it becomes less and less. So that is longitude. And you use latitude and longitude as a coordinate system to define where you're at on the planet. So if you're looking at a chart, and aviators and mariners call them charts, everybody else, they call it a map, and you want to tell your friend where you're at, you'll define your position based on a specific longitude and latitude. I am at 119 degrees west longitude, 29.5 degrees north latitude, and those two lines will connect at your position, at your point. So that is latitude and longitude. Next, sometimes you got to hear this concept called a great circle. Now, what's interesting about great circles is the shortest distance between 2 points on a curved line, on a curved surface, and the Earth is certainly curved, is not a straight line, but a circle. You may be familiar with airplanes that are, say, taking off from New York and flying to Paris. They don't go in a straight line between New York and Paris. They actually go over Greenland or even sometimes farther north. They're called the polar route. And that route, although intuitively it seems like it's a longer distance, is actually a shorter distance because they're taking into effect the curvature of the Earth, and they're finding the shortest distance from point A to point B. That's a great circle route. Boat's the same thing. You want to go from point A to point B, the great circle route is the shortest distance. Now, what is a great circle? A great circle is a line of latitude or longitude that if you were to slice it, it would slice right through the center of the Earth, which means as far as latitude is concerned, there is only one great circle. That's the equator. Everything else is parallel. As far as longitude is concerned, every line of longitude is a great circle. And, something else that might be kind of interesting is Google and look at what they call map projections. In other words, how do you take the curved round Earth and flatten it onto a flat piece of paper? The one that you're probably most familiar with is the Mercator projection, where the lines of latitude and longitude intersect at a 90-degree angle. They're perpendicular to each other. Another one that's interesting, and the reason I mention it here, is the Gnomic chart, Gnomic. It's a great circle chart. So a straight line on that Gnomic chart will actually be a great circle route over the surface of the Earth. It's kind of interesting stuff. I would, highly recommend take a look at it. All right, moving on. What you're going to discover is that celestial navigation works because of a completely inaccurate idea of the universe. In other words, celestial navigation assumes that the Earth is in the center of the universe and it's perfectly round, and surrounding the Earth is this celestial sphere. It's a bubble. And affixed to the celestial sphere are the sun and all the stars and the planets. Incidentally, planet is a Greek word that means wanderer. It kind of moves on the celestial sphere. Again, totally inaccurate, but it works. And we could chat about that a little bit too. So going back to our equator, if you were to put a line on the equator right through the center of the Earth and extend it out to where it intersects that celestial sphere, you would have the celestial equator. If you were to draw a line from the center of the Earth through the North Pole to where it intersected with the celestial sphere, you'd have the celestial North Pole and, of course, the celestial South Pole. You'd have the northern celestial hemisphere. You'd have the southern celestial hemisphere. Everything else is pretty much identical, except the terminology. When you're dealing with objects on the celestial sphere, now you're not talking in terms of latitude, north or south, from the celestial equator up to the celestial North Pole, which incidentally is still 90 degrees, but you're talking about declination. So declination is really the same thing as latitude, except latitude's on planet Earth, declination is on the celestial sphere. And likewise, if you were to extend the Greenwich meridian from planet Earth to where it intersected the celestial sphere, you then would create the 0 degree, what they call Greenwich hour angle, GHA. So you don't have longitude on the celestial sphere, you got Greenwich hour angle. And one of the unique things about the Greenwich hour angle is there's no east or west. It goes west, 360 degrees. That's it. So when I mentioned earlier about east longitude and west longitude being a little problematic, it's when you are now talking about the celestial bodies' Greenwich hour angles, because there is no east or west. So in other words, 90 degrees east longitude on planet Earth is pretty much the same as 270 degrees Greenwich hour angle, or GHA, on the celestial sphere. So sometimes you just got to think about it, and it adds a little complication to the math that we're going to do a little later, but not all that much. While we're at it too, we're talking about, I used the word meridian. So if let's say as an example, you are facing south, and you would take your arm and go from south directly over your head, and now your hand is pointing at north. That line that you just scribed with your hand is in fact your meridian. It's the line of longitude that's directly above you. And some people have heard of AM and PM. Well, what do they mean? AM is ante-meridian, ante being Latin for before. PM is post-meridian, or after. So you got to imagine the sun rises in the east, and it goes up, 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 up until it's at your meridian, that line directly above your head. And then it goes down, 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 down the other side until it sets. So here's AM over here. I can't even do this. I'm doing it backwards. AM over here. Ante-meridian. It's at your meridian. And then PM over here, post-meridian, after your meridian. That's where AM and PM come from. One other thing to mention that it's not really celestial, but it's kind of interesting because it's astronomy. Astronomers talk in terms of declination, north or south of the celestial equator, but they don't use Greenwich hour angle going west. They use right ascension going east, 360 degrees. So in other words, 90 degrees right ascension is the same thing as 270 degrees GHA, Greenwich hour angle. Why they do that? No idea. Absolutely none. What I do know is occasionally if you get one of those apps that tells you the declination, and they will say the right ascension of stars, you need to be a little careful, because that's not the information that you will then need to do your celestial navigation with. You want the Greenwich hour angle. So if you see anything with right ascension, somehow you're going to have to add or subtract 180 degrees from it to get the information that you will need. All right, let's move on. Another concept, zenith. Zenith, by definition, is 90 degrees above you. It's directly above your head. So if you were to take a line from the center of the earth and go right through the top of your head, where it pierced the celestial sphere, that is your zenith. Or in fact, if you were to just look straight up and touch something directly above you on your ceiling, that is your zenith. Another term that you're going to hear about is what they call the geographic position, the GP, geographic position. And that's basically the opposite of your zenith. Imagine you have the sun in the sky, and you draw a line from the center of the sun right to the center of the earth. Where that line goes through the surface of the earth is known as the geographic position of the sun, the GP. And of course, it's going to change throughout the day, but that's going to be an important thing to know. And we'll talk about why later. And now, if you were to look at the distance between your zenith and the geographic position, that's given another name. It's called the zenith distance. Zenith distance. Now, it's difficult to determine or calculate the zenith distance by itself, but what you can do is add another step. with your sextant, which is nothing more than a protractor, you can calculate the angle between your horizon and the sun. So you know the angle between your horizon and the sun. Your zenith distance is between your zenith and the geographic position of the sun. So in other words, if you were to take 90 degrees, that's your zenith, and subtract the angle that you just calculated between the horizon and the sun, the piece left over is the zenith distance. So we'll draw that out. So here's my zenith up here. Here's the sun over here. This is our sextant. And this missing piece will be the zenith distance. So maybe you can see some of that. There you go. So the angle from the horizon to the sun you get with your sextant. You know your zenith to the star, to whatever's above your head, that's 90 degrees. So we're going to take the 90 degrees to the star and subtract this piece in here, and that will give you the other piece, the zenith distance that you need. Oh, come on. Darn thing. Yes, I need better props for sure. That will give you the zenith distance. So it's something that you could calculate pretty easily. All right, let's move on. Another thing you have is local hour angle, LHA. And that's also an easy one to calculate, LHA, because we have Greenwich, and of course Greenwich to your boat, we know what that is. That's longitude. Greenwich to the star, in this case we'll say it's the sun, we know what that is. That's your GHA. The question is, what is it called from the boat to the star? That's your LHA. So again, if I can figure out the reflection here. Oh, for God's sakes. Oh, there we go. So we have Greenwich. We have from Greenwich to your boat, that's called longitude. From Greenwich to the star, in this case the sun, that's your GHA. And the distance from the boat to the sun, that's your local hour angle, your LHA. You're going to use that a fair amount in your celestial navigation. So, what else do we have? We have this thing called Aries. That's a confusing one. Aries is not a star. Aries is the equivalent of Greenwich, but on the celestial sphere. Aries is another reference line for all the stars. So remember, you don't have latitude in the sky going from Greenwich. You have GHA, and you have all the stars. There are 57 navigable stars in the Nautical Almanac that mariners use. And what they found out is that the position between the stars really doesn't change at all. Now, of course, the Earth is revolving all the time, so it complicates things. So they came up with this idea called Aries. So the from Aries, which is a meridian in the sky, to the star, that angle, that distance never changes. So the trick there is to figure out, well, what's the relationship of Greenwich to Aries, and then what's the relationship from Aries to the star? And that gets, as I said, sometimes a little confusing. So imagine Aries as the Greenwich on the celestial sphere. Now, every year they fix that relationship between Greenwich and Aries in what they call the first point of Aries. So as the sun is transiting from the southern hemisphere to the northern hemisphere during our spring equinox, they wait until the sun is directly over the equator. It's 0 degrees, 0 minutes, 0 seconds. At that time, they say, okay, what is the GHA of the sun right at that time. The declination, of course, is 0. But the GHA, what's the GHA of the sun at that instant? And if you were to actually look in the almanac, I've got the 2020 almanac here. The sun actually, the equinox was around March 20, and I know that because you can look at March 20 and you'll see the declination of the sun south, 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 and then all of a sudden it'll hit north. And that happened about 0400 UT on March 20, 2020. But if you were then look at the GHA of Aries at that same time, they're the same. That sets up the first point of Aries. So now, if you want to figure out your GHA to a particular star, it's a two-step process. First, you have to figure out the GHA to Aries, and then you need to figure out the angle between Aries and the star. And that angle is actually called the SHA, or sidereal hour angle. So if you want to find your GHA, your Greenwich hour angle between for a particular star, you'd figure out again, go in the almanac, figure out the GHA for Aries at your particular date and time, and then you would add to that the SHA, the sidereal hour angle, from Aries to the particular star that you want. And if it was more than, 360 degrees, then you would subtract 360 degrees from the result, and that'd be it. So they came up with the idea to make your almanac smaller. This, of course, is your nautical almanac. It changes year to year. This is the one I use for teaching for 2020. I've got the newer ones. But this book basically will have in it the declination and Greenwich hour angle for Mars, Jupiter, Saturn, Venus, the Sun, the Moon, and of course just the GHA for Aries and all the stars. They'll list the SHA and declination for the 57 navigable stars. So just with 6 celestial objects, 4 planets, the Moon, and the Sun, the darn thing is an inch thick. If you now were to come up with the declination and Greenwich hour angle for 57 more stars, this book right here would be about a foot thick. So they said, all right, that's a little unmanageable. So let's come up with this other option. We'll set up a coordinate system, Aries, another line on the celestial sphere, and we can figure out the relationship between Greenwich and Aries pretty easily. And then to that, you would add the sidereal hour angle, the SHA, between Aries and the star. And that's how you get your GHA for a particular star if you're using, navigation at night, if you're using the stars to navigate by. So all that information is going to be in your nautical almanac. Finally, the other thing that you'll have, and we'll talk about these in a little more detail, is publication 229. That's the site reduction tables for marine navigation, not to be confused with publication 249, which is air navigation. I know a lot of mariners use both. They ultimately got to give you the same information, but it's just slightly different in how you enter them and how they work. So again, some of the terms, there's latitude, longitude, great circles. We talked about the celestial sphere, declination, Greenwich hour angle, GHA. We mentioned right ascension. We talked about zenith, the geographic position, GP, zenith distance, local hour angle, Aries, and sidereal hour angle. Now, before we go on, real quick, why is it called Aries? Because when they started this, the sun was actually in the constellation of Aries. It's not there anymore. Right now, it's actually in the constellation of, what is it? I want to say Pisces. And it's actually moving very quickly into the constellation of Aquarius. So if they were to name it today, it wouldn't be named Aries. It'd probably be named Pisces. So again, it's another reference. It's the prime meridian on the celestial sphere. It's another reference point. But that confuses people because they assume it's a star. It is not a star. All right, moving on. What else? So, some of the toys that you're going to need for celestial navigation. Of course, I showed you the one, your nautical almanac. You're going to need a nautical almanac. Now, these change every year, unfortunately. And the reason they change is, well, just think about it. The Earth revolves 360 degrees, but it does so in 365 days. So the math does not quite fit. There's always going to be a little extra in there. I've had people say, well, maybe they repeat itself. The almanac repeats itself every 5 years or so. I don't know that to be true or not. I have no idea. What I do know is, having used different year almanacs to solve problems, they're not significantly different from one another. Maybe a few minutes here or there, but for the most part, it's not like, they're 30 degrees off from one year to the next. So having said that, if you have an older almanac, you're probably fine to use it. It will work. The other thing, of course, that you're going to have is publication 229. This is the Sight Reduction Tables for Marine Navigation. Essentially, all it is a computer for solving spherical triangles. It allows you to do what they call a sight reduction, specifically using what is known as the Marc St. Hilaire altitude intercept method. Now, Marc St. Hilaire is the name of a guy. You can Google him as well. Saint St. Hilaire, Helaire, I think, or something. It's kind of an interesting read. There are other altitude intercept. There are other sight reduction methods that you actually can use. I'm aware of at least 6 of them. This is the one that I'm most familiar with, and it utilizes Pub 229. Now, you also hear a lot of people talk about publication 249, which is the Air Almanac, and that also works. It's set up a little differently. Pub 229 is more accurate. Pub 229 has 6 volumes based on latitude. Pub 249 has 4 volumes. It's not as accurate, and it was designed to meet the unique needs of aviators. If you think about World War II bombers, they'd start off from a boat or they'd start off from an airfield, and they'd basically just fly out in a straight line, generally at night because they're harder to see, and they drop their bombs, and they turn around 180 degrees, and they'd fly a straight line back to where they started from. So the way that the airplanes would work, first of all, they had a kind of a unique sextant on the top of the airplane. It was more like a periscope, and they would predetermine these things. They would say, okay, we have a star and we should see it at this angle, and there's another star and we should see it at that angle. So they would pre-calculate these, and then they just look in their sextant and say, well, there's that star at that angle. Good, we know where we're at. There's that star at that angle. We know where we're at. And and also it allowed them to determine their ground speed, which was important because of fuel burn. Because they would say, well, before we get to this point, we should get there in 35 minutes. And the next point, we should get there in 30 more minutes. So not only will they be able to use the stars at night to navigate, but it would also indirectly help them determine their ground speed and how much fuel they're burning. So as a result of that, the Pub 249 tends to be very friendly towards star navigation. Again, as we'll see here in a bit, it ultimately will give you the same information that 229 gives you. It's just set up for a slightly different purpose, and it's a little bit different to use. What else do we need? Well, a set of parallel rulers is always nice to have for any kind of navigation, but we'll show you how to use these. A pair of dividers are nice to have for navigation, and we'll show you that as well. A universal plotting sheet. These you could buy in packets. And with this, this is an example we'll talk about later. You can set up your latitude and longitude and your bearing from your assumed position, your AP, to the sun, and as a consequence, come up with your line of position, the perpendicular line. These are useful, very useful. And let's see, a watch. You need a watch of some sort, also known as a chronometer. I could barely say that. And finally, of course, a sextant. This is the what the heck? Well, Astra 3 that I have. It's not a bad sextant. It's a metal one. My dream is the Sessions and Plath sextant. That would be awesome. I see a lot of people ask about their quote unquote plastic sextants, the Davis sextants. They work just fine, especially for the type of navigation that most of you will be doing. There's no problem with the plastic, and everybody says, "Oh, if it gets too hot, it's gonna warp and change things." Probably not. I will say that I get most of my stuff through a company here in the United States called CelesteAir.com. CelesteAir.com. And this is not necessarily a plug for them. It's the truth. They probably don't even know I exist. But they have everything celestial. So whether you want to get the almanac, the Pub 229, Pub 249, sextants, a watch, parallel rulers, dividers, universal plotting sheets, they have it all. I highly recommend you could take a look at their website. Additionally, what I noticed the last time I was on there is that you could actually download the Pub 229 and the Pub 249 for free. And I'd recommend you do that, if nothing else, just so you could see the differences between the two. Now, having said all that, you could also download the Nautical Almanac. I just like the paper because I know where things are in those books, and it takes me just a second to flip through it and find the information I want. What I've noticed when I download things on my smartphone or my tablet is I gotta scroll and scroll and scroll and scroll and scroll, and then I get one part, and then I gotta scroll back to the other part. I find it kind of a annoying pain in the butt, to be honest with you, but that's just me. But anyway, CelesteAir.com. Take a look at their stuff, and you can download the Pub 229, Pub 249. I don't know if they have the Almanac, but you could always Google that. I've seen those downloadable in lots of different places. So those are the tools that you'll need. So let's talk a little bit about what you're actually attempting to do. I got to get a camera so I could do this better. So we'll talk about circles. And this is a thing, we're going to call it, over here, trilateration. You can look that up. So assume that we know a position of something, our geographic position, and we know the distance we are away from that thing. We can then use that distance as the radius of a circle and draw a circle around that known point. So what does that tell us? Well, we've got to be somewhere on the circle. We could be here. We could be here. We could be over here. We don't know where on the circle we're at, but we do know we are someplace on that circle. We have to be. Now imagine that you had a second point that you could do, and you do a circle around that. The point is your geographic position. The radius of the circle is your zenith distance. Well, in theory, that circle may intersect with the first circle in 2 points. So that means you're either going to be at point 1 or point 2. It's a lot better than, an infinite number of points. Finally, let's say that we had a third circle and we did the same thing. Well, hopefully those 3 circles will intersect at 1 point. That 1 point is your fix. That is where you're at. And this, using circles, again, is called trilateration. It actually is pretty cool. And lots of things use trilateration. As an example, if it's a earthquake and you're trying to figure out the epicenter, they use circles, trilateration. A GPS uses circles, trilateration. Now the GPS is a little different in that imagine an ice cream cone with the pointy end of the cone being the satellite. And the satellite will send out electronic signals and time them, the time it takes to go from the satellite, bounce on the ground, and go back up to the satellite. So that circle they're drawing is not necessarily a known distance from a known point on the ground, but it's based on time. A circle drawn from equal time it takes for a radio signal to bounce from the satellite to the ground and back, and it can draw a circle. And so GPS uses trilateration as well, and in fact, a GPS fix, I believe, as a minimum of 4 circles. Some of them are even more, and everybody uses GPS nowadays. But in theory, it's not all that different from how a sextant works. Now down the road, we're going to mesh that concept in with another concept, triangulation. So let's imagine that you're coastal cruising and you look out and there's a lighthouse and you think, aha, I'm going to get out my compass and I'm going to shoot a bearing from the boat to the lighthouse. And that bearing, say, is 090 degrees. So your compass says the lighthouse is due east of you, which means, of course, that you are due west of the lighthouse. So now at least you know what line, what bearing you're on, but you don't know how far away from the lighthouse you are. So perhaps you're coastal cruising and you see another object, a building or a mountain, and you do the same thing. You shoot your bearing to the building or the mountain. Well, where those two bearings cross will be where you're at, your fix. And you need to do that because even though you know the line that your boat is on, you don't know the distance from that point that you are at. However, you can do something else. Let's say that you know the height of your lighthouse. Well, you know this angle here is 90 degrees. This angle over here is what you got with the sextant. So trigonometry says, well, if you got 2 angles and a distance, you can figure out this distance and that distance. So you actually can use trigonometry to figure out your distance from that lighthouse to figure out your position. And that's kind of neat. And that's really the basis of that Mark St. Hilaire altitude intercept that we'll talk about here in a little bit. Now, one of the guys I just loved, and a lot of the information, a lot of the problems I've taken directly from his webs when I was trying to learn this, was a U.S. mariner. His name was Chris Nolan, and I always remember Chris from Sailing Vessel and Navigator. And I think his series is Practical Navigation. He's the guy that came up with this idea. Well, he didn't come up with the idea, but he coined the phrase lighthouse in the sky. Let's say that you're out in the middle of the ocean and you can't see an actual lighthouse, but imagine that the star of the sun is just a lighthouse in the sky. You've got the same basic idea, the same basic triangulation that you can use with celestial objects. They're just not a physical lighthouse, but well, you get the idea, the same idea. And Chris, as far as I know, he talked about that quite a bit. You really ought to watch his series. It's fantastic. And someday maybe I'll have the privilege of running into him and thanking him for essentially teaching me how to do all this stuff, because he was the man. He was the guy that I learned from. So again, the big picture is circles, trilateration. With your geographic position and the zenith distance, you could draw a circle around that. You're somewhere on that circle. You get 2 circles, and they intersect in 2 places. Well, you're either point A or point B. You got 3 circles. Well, hey, if they all intersect at the same place, that's where you're at. That is your fix. And as I said, GPS and everything else works basically the same. And, triangulation, we talked about that a little bit. The only thing else to talk about is when you're talking about a direction on planet Earth, it's generally called a bearing to the lighthouse, bearing from the lighthouse. Aviation changes a little bit. It's generally a radial from the lighthouse and a bearing to, slightly different. But if you're talking about a line or direction on the celestial sphere, they don't call it a bearing anymore. Now they call it an azimuth. So it's the same idea, just slightly different word. Um, Talk about something else a little bit. The relationship of time to distance. That's another interesting problem. Um, yeah, and that was John Harrison. There's a guy you ought to look into. The 1714 Longitude Act. And John Harrison, born 1693, died 1776. He's the Scottish clockmaker carpenter that solved the longitude problem. So here's what was happening. You know, most navigators, and we're going to talk about this here in a minute when we get into the noon sight, map makers for a long time knew latitude and longitude. The problem is when you're away from shore, it's kind of hard to figure out where you're at. So latitude was the easiest to solve. The merchant mariners back in the 1700s or even earlier would basically from Europe, say to the Caribbean, would follow the coastline down to Africa, get to where a known latitude was, and then pretty much make a 90-degree turn to the right. And if they could follow that same line of latitude across the ocean, they'd end up, in St. Lucia, wherever the heck they were going to. The problem with that, though, is pirates also knew that. So pirates would just sit in strategic places along these coastal routes and wait for these ships to come down and then go out and ambush them and take everything they had, and that was that. So in 1714, the Brits came up with this idea. They said, we got to come up with something better because we're losing a lot of money here. And at that point, they could deal with latitude. Longitude was completely different. It was very difficult to determine your longitude in the ocean. So John Harrison, the clockmaker, he had an idea. He said, let's use time. He said, the Earth rotates 360 degrees in a day, and there are 24 hours in a day, which means every hour the Earth has rotated 15 degrees. So he came up with the idea. He said, if I can make an accurate, small enough watch such that you, at any given time, knew the time in Greenwich and knew the local time, you can compare those two times and then work off the, 15 degrees per hour thing and figure out your actual longitude. And initially everybody laughed at him because it was all the academics of the day that were looking at the moon and looking at all these other things. And here's this basically unknown guy that says, hey, I got an idea. Let's use a clock. And he was laughed at for years. But in fact, he was 100% right. And just as I said earlier with the GPS and trilateration, what do they use? They use a clock. So John Harrison was 100% right. There is a direct relationship between time and distance. And that's another thing that, I would highly recommend you look into. Google John Harrison. Google in search of longitude. Very, very fascinating part of history. It's really worth looking into. While we're here, let's talk a little bit about precision. How accurate do you need to be when you're doing celestial navigation? Well, I guess it just depends on what you're trying to do. If all you're trying to do is hit a continent, you could be somewhat inaccurate and still get there. If you're trying to get through a reef field, well, you probably want to be a little more accurate. If you're working on some academic test for, the U.S. Coast Guard or the Royal Yacht Association or something like that, you got to be really accurate. So precision is really determined by what your goals are. For most sailors, you don't have to be super precise. Although, having said that, you're always striving to be more precise, and we'll talk about that in a little bit. So let's move on to the next thing, the noon sight for latitude. Probably the earliest method for navigating across oceans. And in fact, if all you knew how to do was a noon sight for latitude, you can be perfectly safe crossing an ocean. It's not a big deal. So again, the idea was you get to a known point of latitude, and now you're crossing the ocean and you want to be at that same latitude on the other side. Well, every day you take this sight and you determine whether you're still at that same latitude or not. If you are, good. If you're slightly north, as an example, well, you'll have to correct back to the south. If you're slightly south, you'll correct back to the north. But each day you're doing the same thing. Now, it's called the noon sight, not necessarily that it's done at noon, close to it, but it's done when the sun is on your meridian, when it's above you, when it's on your same line of longitude. That's when you got to do the noon sight. As I said before, the sun comes up in the east, goes up, 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 up to a high point, and then it goes down, 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 down. You got to do your noon sight when the sun is at its highest point in the sky, when it's on your meridian, when it's on your line of longitude. That's when you will do your noon sight. Now, the almanac will give you an idea of when that is. It's called MERS, or meridian passage. And of course, we know the meridian. We described that before. If you're looking south, arm to north, it's that line that you just described with your hand. That is your meridian. But you can also just do it mechanically. In other words, you get an idea of when you think the sun's going to be the highest point in the sky, and you go out with your sextant and you get the angle, you get the height, the HO. We'll talk about that in a minute. And you do another one a few minutes later. Well, it's either going to be increasing or decreasing. If it's increasing, well, you're not at your meridian passage yet. So let's say you go out and your sextant says 60 degrees, and then it says 61, then it says 62, and then 63, and then 62, and then 61. Hold on. 63 was the meridian passage, the MERS passage. That was when the sun was the highest point in the sky. So that's when you will do your your noon sight for latitude. And the good part about that is there's only two variables that you'll have to deal with. We'll talk about it. One is zenith distance, the other is the declination. And there's only three possibilities. So it becomes pretty academic, pretty simple. The declination of the sun, you're going to get right out of the Nautical Almanac. Yep, that's better. So you want to get the declination of the sun for any particular day and time, you go in the Nautical Almanac. It's going to tell you that. The zenith distance you're going to get by firstly taking your sextant out and figuring out the angle between the horizon to the sun, and then secondly taking your zenith, which is 90 degrees, and subtract from that the angle that you got with the sextant. What's left over is the zenith distance. And once you have those two pieces, you're set up. So, again, there's only three different possibilities. One possibility is that the sun is in one hemisphere and the boat is in the other hemisphere. The second possibility is the sun and the boat are in the same hemisphere, but in this case, the boat is farther away from the equator than the sun. And the third possibility is the sun and the boat are in the same hemisphere, but the sun is farther away from the equator than the boat. That's it. Those are the only three possible outcomes when you do a noon sight for latitude. So let's take as an example. And again, if you have questions, I'll give you my email. I'm going to do subsequent videos with a lot more detail and a lot more problems. This is just kind of a quick overview of what you can expect to happen. But let's say that it is, if I could get this out here, let's say that it's August 4th, 2020, and you're somewhere in the Eastern Caribbean. Actually, let's not do that one. We'll come back to that. My mistake. Let's do an easier one first. Let's say it's November 10, 2020, and you're somewhere in the Yucatan Peninsula. And these I just grabbed from Chris Nolan, poor guy. And it's 1800 UT, and your HO, we're going to define that here a little bit later, is 49 degrees 15 minutes. You got to figure out your latitude. Well, you need to know the two variables. You need to get your declination, your zenith distance. So you go into your nautical almanac, look up November 10, 2020, look at 1800, and it says declination is south 7 degrees 24.8 minutes. We'll just say 24 minutes. Not even going to worry about the 8, because at this point you don't need that accuracy. Now, your zenith distance, of course, is 90 degrees minus the HO of 49 degrees 15 minutes. Interestingly, 90 degrees is exactly the same as 89 degrees 60 minutes. That is 90 degrees. So we have 89.60 minus 49.15. So that gives us our zenith distance of the difference between 40 degrees 15 minutes. So then you can diagram it, and the declination is the equator down to the sun. Zenith distance over here is sun to the boat. I'm going the wrong way. Sun to the boat. We want this piece in here. We want the latitude. So it's going to be the zenith distance minus the declination will give us our latitude. So we just plug in the numbers. Zenith distance was 40 degrees 15 minutes minus, it should be south 17. I'm sorry, I said 7. That's the problem. Minus south 17, I rounded up to 25. So that gives us our latitude of 2320. So yeah, just notice that from the book, that should actually be 17 degrees south, 24.8, which we rounded up to 17.25. So those are where the numbers came from. So, latitude in this case is the zenith distance minus the declination gives you your latitude. Super, super easy. Two variables. Once again, that's all you do. Let's look at a different one. Make it a little more interesting. Let's say that it is September 1, and we're somewhere off Nova Scotia, and it's 15:30. Well, what you're going to discover is the almanac only deals in whole hours, 15, 16, so forth. So this is 15:30. That complicates things a little bit. Again, our HO, 53.24.7 minutes. We can round that to 53.25. Make it easy on yourself. The more accurate, of course, we wouldn't round it off, but in this case we are. So now we've got to figure out how to deal with the in-between, the 30. Well, you got two ways to do it. One is 30 minutes is halfway between 1500 and 1600. So you can, look in the almanac and find the declination for both 1500 and 1600 and cut the difference. The other thing that you can find in the almanac is if you were to follow the declination columns all the way to the bottom, you'd find this thing called a D number. And if you read it, it says D is 0.9. Now, the 0.9 is the amount of change per hour of declination. So now with that 0.9 D number, you could actually go in the back of the almanac and find this section called increments and corrections. It basically will be set up by minutes. There'll be one for 1, 2, 3, 4, all the way up to 59. So you'd look for 30 minutes, and the fourth column you'll see the D, and it'll say, hey, if the D is 0.9, that is a 0.5 correction. So in other words, you've got to go to your initial declination and correct it by half a minute, basically. Make sure that you know that you're either adding it or subtracting it. In this case, we're adding it because at 1500 the number is smaller, the declination is smaller than at 1600. So then we can diagram it. no problem. We have our latitude up here, we have the declination of the sun, and the zenith distance between the two. So in this case, the latitude is going to be the declination plus the zenith distance. So we just add the two together. 36.25 for our zenith distance, which was, again, 89.60 minus 53.25 from here. That gave us 36.25, and we add the declination of 7 degrees 57 minutes, and that gives us 43.82. Of course, we can't go more than 60 minutes in a degree, so that's the same as 44 degrees 22 minutes north. And again, we said we were up by Nova Scotia, so yeah, that pans out. Once again, simple math. Let's talk about the third possibility, and that is another problem. Let's say that it's August 4. We're in the Eastern Caribbean. It's 1618 UT. HO, our sextant height of sextant, is 86 degrees 53.3 minutes. We can round that off. Got to find the latitude. Well, we go into the almanac at August 4, 1600, and we find that declination is north 16 degrees 59.4 minutes. The D number is 0.7. We go in the back of the book to the increments and corrections. We find 18 minutes, and we see that if the D is 0.7, the correction is 0.2. So our corrected declination is north 1659.2. We subtracted it because from 16 to 1700, the declination is decreasing. Our ZD, our zenith distance, is of course 90 degrees, 89.60 minutes, minus 86.53. So that's 3.07 is the zenith distance. And we map it out and we say, okay, so the declination, the latitude, the zenith distance. So the latitude is going to be, in this case, the declination minus the zenith distance. 16.59 for the dec minus 3.07 is 13 degrees 52 minutes north. And we have, what do you know? We have our latitude. And that's all that you're doing. There's only three possibilities. Again, sun in one hemisphere, the boat in the other. Sun and boat in the same hemisphere with the boat farther away from the equator than the sun. Sun and boat in the same hemisphere with the sun farther from the equator than the boat. And that will determine what you do. In the first case, it's zenith distance minus dec. Second case, it's zenith distance plus dec. Third case, it's dec minus zenith distance. So once you find those two variables, you're set. Now, there are two special cases that are worth talking about. One is the vernal equinox, spring equinox, where the sun is directly over the equator. In other words, the declination of the sun is 0. So that's easy. Your latitude is just your zenith distance. The other one is what they call Lehanten noon, when the sun is at your zenith, in which case the zenith distance is 0. So your latitude is going to be the declination of the sun. But going back to Tropic of Cancer, Tropic of Capricorn, that will only work if the sun is between those two. In other words, if you're in Auckland, New Zealand, or Nova Scotia, you'll never have the case where the sun will be at your zenith. So that will never happen. Why we're talking about this, we're throwing out some concepts of HS, HA, HO. So HS is height of sextant. So if I just take my sextant out and I figure out the angle between my horizon and the celestial body, that is HS. Now I need to correct it, and there's two corrections that need to be made to get to HA. One is called index error. It's a compass correction. The other is called height of eye. Start with the height of eye first, also known as dip. In other words, the sextant sighting that you're taking should be from the horizon, should be from the surface of the water. you're probably standing on your boat. In my boat, that puts me about 9 feet above the water. So, in the first page of the Nautical Almanac, which is why I like the book, I could go right in here, first page, if I can figure out where the heck it is. And it has this section over here called, called dip. Here's dip over here. It's dip right there, first page. And basically it'll say, hey, if you're standing 9 feet above the ground, your correction is minus 3 minutes. It's always going to be a minus correction. So I have to deal with that. The next part is the index error on the sextant. Some sextants, the mirror itself is, half of it is mirror, the other half is clear. And in theory, the horizon should be the same on both. If you find one slightly above the other, you've got to correct that. And since a lot of people have heard some of these terms, the way you correct it with your sextant is to rotate this knob. By rotating this knob, I'm going to get those two broken horizons to be the same. Now, I read the index error from the knob, 1 degree to or minute, 2 minutes, and so forth. But more specifically, if I'm rotating that knob and it's going, say, from 1 to 2 to 3 to 4 and that stuff, it's what they call on the arc. And we need to subtract that. On the other hand, if I'm going, say, 59, 58, 57, it's what they call off the arc. I need to add that. And if you're not quite sure what's what, you got that little memory item, I have there. If it's on, take it off. I mean, if it's on the arc, subtract. If it's off, put it on. If it's off the arc, add the darn thing. So let's say that we have 2 minutes on the arc, index error, and we have 3 minutes dip. So the first thing we'll need to do to get from HS, our height of sextant, to HA, our parent altitude, parent height, is to subtract 5 minutes from what we originally had as HS. That will give us HA. And now with HA, you can do the next correction that will get you to HO, which is your observed height. The correction between HA and HO is the only one that will differ depending on which celestial body you're looking at. So, the sun has one correction. Planets maybe have 2. The stars have 1, but it's different one from the sun. The moon may have 3. In the case of the sun, let's say you have an HA of, 60 degrees, and you'll go in once again into the almanac, first page, and it will have the main correction over here, main correction. And what that is doing is, instead of just having the lower curvature, probably of the sun on the horizon, like the bottom of the glass, instead of having just this piece on the horizon, if I could figure out how to get this going, because it's all backwards, instead of having the bottom part on the horizon, you want to get right in the middle. So that main correction that you'll get out of the almanac will correct for that. And, it'd probably say something like add 17 minutes. Based on your HA, now you got to add 17 minutes. So you get your sextant HS, you do the dip, the height of eye, and the index error. Maybe that subtracts 5 minutes. And then you now could go to your HO and it'll say, add 17 more minutes back. But if you just follow the steps, eventually you will end up with your HO, which is your observed altitude, your height observed. And that's really the one that you want. Okay, my goodness. More and more and more and more. Let's go on to another thing. And again, this is just some basics. You just do lots of problems in practice. Nothing is going to change from what I'm telling you It's just going to be easier and you'll understand these concepts better. Polaris is going to be unique, the North Star, because it's the only star that's roughly directly above the North Pole. Not quite, because the Earth wobbles a little bit, so it's a little variable. But for the most part, it's above the North Pole, and you could use it for determining your latitude. Of course, if you could see Polaris, and you can only see it if you're pretty much in the northern hemisphere. When I was in Panama, I don't even think I could see Polaris in Panama. I think it was too low on the horizon. But regardless, it's a formula. If you want Polaris, it's a formula. It says, hey, you have Polaris is your latitude, HO, minus 1 degree, plus A sub 0, plus A sub 1, plus A sub 2. A sub 0 is the LHA of Aries. A sub 1 is latitude. A sub 2 is the month of observation. So what you do there is you go into your almanac, and towards the back, there are 3 pages that deal with Polaris. Once again, trying to figure this out. Okay, there it is. It deals with Polaris. Polaris, and it will tell you, it has the 3 sections down there. The top part is A0, A1, and my pinky down here is A2. You just follow the formula. The formula is actually there. So, as an example, let's say that, we'll try this one. Let's say that it is October 25, 2020, 0500 UT. We go in the formula, HO minus 1 degree plus A0 plus A1 plus A2. We have our DR, dead reckoning latitude of 44 north. We have our DR longitude of 4030. That's just our best guess as to where we're at. So we go into the almanac and we find our GHA of Aries, which is 10902, and the LHA is going to be that's essentially from Greenwich. The LHA is going to be from the boat to Aries, so we need to subtract our DR longitude, give or take, and that will give us the LHA of 69. So 69 degrees is the difference between the boat and Aries. 109 is the difference between Greenwich to Aries. We don't want that. So 69, we have the latitude, the month. We go into the almanac and we find all the numbers. 44 degrees, 30 minutes. Minus 1 plus 23.4 plus 0.6 plus 0.4. So we end up with a latitude of north 44 degrees, 47.3 minutes. It's, you do them a few times, it gets pretty easy. It's just, there's a formula, a literal formula. You just follow it. As I've done this, and when you look at the information in the back, the worst case scenario, biggest correction for Polaris might be adding between A0, A1, A2, you're adding 1 degree 45 minutes. So if you think about the formula, you first subtract 1 degree, then you got to add 1 degree 45 minutes at the worst possible correction. So really, if all you did was just use your HO, you wouldn't be more than 45 minutes off 45 nautical miles. Now, I'm not suggesting you do that all the time, because obviously this is a game of precision, but it would work. You're not going to end up on the other side of the planet someplace. You're going to be a reasonable distance from your actual latitude if you just use HO and don't even, maybe you forgot the formula, although it's written in the book. All you got to do is look at the book. So again, Polaris is pretty fun. It's an easy star. It's a dim star, but it's in a very black part of the sky. So you'd find the Big Dipper, Ursa Major, and the part of the Dipper that's going up. You just kind of follow that 3 times the distance between the 2 stars and the Dipper, and what do you know? There's that rather dim star in the black patch of sky known as Polaris. It's an easy one to find. You just look for it a few times and you'll figure it out. So, again, it is just a Yeah, it's a formula. Just remember the formula. All right, that leads us to the last thing, solving for latitude and longitude. And it's a 5-step process. It's actually pretty simple. Here are the 5 steps. Step 1, you want to determine HO. Well, we already did that. We know how to do that. Step 2 is you want to determine the GP of the celestial body. That's the X in the trilateration. And you go into your almanac and you figure out the declination and you figure out the GHA for that particular time, and that is your GP of the celestial body. Step 3 is we want to enter into our Pub 229, publication 229. And to do that, you need 3 pieces of information. You need the LHA, local hour angle, you need your latitude, and you need your declination. All of which to a whole degree. No minutes, just a whole degree. So it's a big fudge factor. You get latitude, that's your best guess, declination out of the almanac, and your LHA, depending on whether you're in the eastern hemisphere or the western hemisphere, it's going to be the GHA minus where your guess is, or GHA plus where your best guess is. As I said earlier, when the Brits came up with east and west longitude, they complicated things a little bit. Now that you got step 3, you could go into Pub 229. Step 4, you're going to get HC, not HO. HC is the calculated height. That's what the mathematicians say the angle should be if you're actually where you're at. You'll get a D number. That's a correction for the minutes of declination that you did not originally use. Remember, the declination is to a whole degree. And ZN, which is basically your bearing from the boat to the sun, and you'll switch it back the sun to the boat, and that puts you on that line. Remember the lighthouse in the sky we described earlier. And then finally, step 5, you're going to compare your HO with the HC from Pub 229, and you're going to decide which one is bigger, and that will then tell you whether you need to go towards the sun or away from the sun to find your actual position, and you'll plot it on the universal plotting sheet. So those are the 5 steps. Actually pretty simple. So let's run through these pretty fast. We'll show you how some of this stuff works. So let's say that it's March 11, 2020 at 2000 UT. We're somewhere between Panama and the Marquesas Islands. And we take our sextant out, we find an HO. We've gone through the steps, HS, HA, HO, 61 degrees, 55.4 minutes. Notice our DR latitude, where we think direct reckoning latitude is 5 degrees, 20 minutes north, and our direct DR longitude, 90 degrees, 25 minutes west. That's where we think we're at. So we go through the steps. Step 1, again, determine HO. Well, we know that. 61 degrees, 55.4 minutes. And we could round it off if you want to 61 degrees, 55 minutes. Step 2, determine the GP of, in this case, the sun. Well, we go into the almanac and we find out, hey, the declination is south 3 degrees, 19.3 minutes. And the GHA is 117 degrees, 33.1 minutes. Those I picked right out of the almanac. So now we've got 2 of the 5 steps done. So now we can go into step 3. Man, I'm always going the wrong way. So step 3, if you remember, we want to go into Pub 229. And we need to figure out the LHA, the latitude, and the declination to a whole number. So remember, the LHA is going to be in the Western Hemisphere, the GHA minus our the LA the GHA minus our DR latitude, and it needs to be a whole degree. And remember, our DR latitude was just a guess. Originally, we guessed we were at 90 degrees 25 minutes. So let's say, make another guess. Let's say we're at 90 degrees 33.1 minutes. So those two will cancel each other out. So in other words, our LHA of 117.33.1 minus our best guess of 90 degrees 33.1. So our LHA is 27 degrees. That's one that we need. Latitude. Remember, we were in the almanac, or actually we from our step 1, we determined our latitude was 5 degrees 20 minutes north. So closest is 5 degrees. Declination. This is the one. We went into the almanac, and at that time our declination was 3 degrees 19.3 minutes south. So 3 degrees will be our declination to a whole number with a remainder of 19.3. So those are the three pieces we need. Latitude 5, declination 3, LHA 27. So now with that, I can go into Pub 249, which is just a computer for solving spherical triangles. That's all we're doing. And we open up to the page we want of latitude, LHA rather, of 27 degrees. We find that, and then you got to find two sides. One side is going to say same, and this one will say contrary. Now, if the sun and the boat are in different hemispheres, it's contrary. So we're actually going to be using this page over here. So we have an LHA of 27. It says that in the top. We go to our declination, our latitude rather, of 5, and we go down until we hit the declination of 3, and now we can pick out some numbers. And the three numbers we're going to pick out, of course, will be HC, the calculated height, the D number, and ZN. So HC will come out as 62.08 right out of the book. D, the D number, is minus 16.1, and Z is 103.9. Now the first thing we can do is to change Z, which is sun to the boat, to ZN, which essentially is boat to the sun. And there's a formula right in Pub 229 on each page. I can read it. It says, if the LHA is less than 180, ZN is 360 minus Z. So our LHA, of course, was less than 360. So, excuse me, our ZN is going to be 360 minus Z. So our ZN will be 256.1. So we have the information. We have our HC, 62.08, the D, minus 16.1, and ZN, 256.1. Now, the D number deals with the added minutes that we did not use off our declination. That's going to change the HC very slightly. So I guess we can deal with that right now as well. And think of it in terms of a ratio. The minutes are 1/60th of a degree. So in this case, we're going to take the extra minutes that we didn't use, and that was 19.3 minutes off the declination that we got out of the almanac. We're going to divide that by 60, and then we'll multiply that number by minus 16.1. So basically that number will be 5.17 minutes. And since it's got the minus sign, we're going to subtract that from our initial HC to get our corrected HC. So our corrected HC is actually 62 degrees 2 minutes. So now we're done with Pub 229. We're done with step 4. And now we can finally go into step 5. And step 5 is we want to compare HO to HC, and then figure out which one is bigger. So in this case, we know that HC is going to be bigger. HC is 62 degrees 2 minutes. HO was 61 degrees 55 minutes. So HC is actually bigger by 7 minutes. And so that's good to know. And now we got to figure out, well, are we towards or away? And if you can't remember that, you can use the memory item of CGA or HOMOTO. CGA stands for calculated greater away. HO more, MO, towards, HOMOTO. So since HC is greater, we are going to be away those 7 minutes. So what in God's name am I even talking about? Pretty simple. Now we take out our universal plotting sheet, and we're going to think in terms of which information did we use in our step 3 to get into it. So remember, 90 degrees west is the midpoint, and we put in 89 and 91. 5 north is the midpoint, and we have 4 north and 6 north over there. We figure out our assumed position, the AP. If you recall, that was, what did we use in step 3? Well, we said 5 degrees, so all right, there's 5. And we said 90 degrees, 33.1 minutes. So that AP tick we have there happens to be 5 degrees north, 90 degrees, 33.1 minutes. You just ask yourself, hey, which numbers did we use in step 3 of the 5-step process? Now, remember ZN, 256. That's where that parallel ruler will come in, because we could use this magnetic compass to our advantage, but notice we have to use it from the exact center, which is here. So we can use the parallel rulers from the center through the 256. That will give us our bearing to the sun, and then by moving them, splaying them out, we can now move it from the center to where the actual boat is, and draw that line. That is, I gotta do it, get it right. That's this line right here, right to the sun, and extend it that way. So our AP, remember, we are now 7 minutes away. So from the AP, we take our little dividers and we figure out from here on the line, the bearing, we've got to go, let me get this a little bit, we've got to go 7 minutes, and we could get the 7 minutes here on the latitude. So it's going to be, God, this is very awkward doing it backwards. I can't think like this. We go 7 minutes away because of CGA, and then we draw a perpendicular line. This perpendicular line right here, that is our line of position. Essentially what that is it's a tangential line to a point on the circumference of the circle. Remember the trilateration. So that's it. And if we want to know our exact location, we would then go to our line of position right there, and we take out our dividers and figure out the exact latitude and longitude at that point. And we find out that that point is actually 5 degrees 02 north, 90 degrees 26 west. So that would be your actual location. Now remember, the latitude lines are only correct basically at the equator. As you go farther north or south of the equator, these lines get smaller. So what we can do down here is we have our 5 degree mark, that's the latitude we're at, and we can figure out the actual width between these. And that's what I just did up here. I now have the width. I put a tick mark and a tick mark and a tick mark and a tick mark so I can draw my lines of longitude. But this is what the universal plotting sheet is used for. And you could use this multiple times. I mean, if you do it in pencil, you can erase it. Um, it doesn't have to be 1 degree increments. It could be 2 or 3 or whatever you want. I mean, they're actually very useful, and it's a way to, basically you're still using the trilateration, you're still using the circles, but your line of position is essentially a tangential line on the circle, and it works fine. And just for grins, if you ever were so inclined, you could actually do the direct calculation, in which case, your HC is sine L sine D plus cosine L cosine D cosine LHA, where L is latitude, D is declination, LHA is the LHA. I mean, so if you didn't have Pub 229, Pub 249, but you had a trigonometric calculator, you could still come up with this stuff. That's how they do it anyways. And if you're so interested, the azimuth, which is your ZN, that's how you'd find that. same idea. So remember too, we were using Pub 229. I mentioned Pub 249 will have the same information. It'll give you a HC and ZN. It's a slightly different book that you're using. Anyways, so those are the concepts. You have the definitions that are slightly different: latitude, longitude, declination, GHA, LHA, zenith, geographic position, zenith distance, Aries, SHA. You've got the toys, a sextant, a watch, dividers, parallel rulers, of course, the almanac, Pub 229, most likely. You know a little bit about the noon sight for latitude. Now, thinking about that too, let's that's interesting, because I didn't mention that, but we might as well. Basically, what we're doing is setting up a triangle, a big triangle. So if we have planet Earth, terrible planet Earth, and there's our equator. So here's the North Pole. Let's say our boat's over here, and we have the sun over here in the morning. So we have a triangle that we're setting up. Now this angle, that's LHA. We know the length of this line because we know the declination. This is the declination. This is what they call the codec, which is going to be 90 degrees minus the declination. This is our zenith distance. So we have the length of this line, the length of that line, we have that angle. So we can solve this as a trigonometry problem. And this triangle is going to change throughout the day. The sun rises in the east, and as it goes towards our meridian, it's going to get closer and closer to the boat, and eventually at one point collapse into a straight line where the boat and the sun will be on the same line of longitude, on the meridian. And then it will start to expand in the other direction. So I mention this because, again, when are you doing your noon sight? Well, when that triangle collapses into the straight line, when it's in fact on your meridian. Otherwise, you're using the triangle. So the noon sight is a very special case of a normal sight reduction, because it happens at that one time when your triangle collapses into a line. And then, as I said, you've got the two variables. You got declination, zenith distance, and you've only got the three cases: sun, boat, different hemispheres, sun, boat in the same hemisphere, with the boat farther away from the equator of the sun, or the sun farther away from the equator than the boat. Not a problem. We talked a little bit about Polaris. It's just the equation. Your HO minus 1 degree plus A sub 0 plus A sub 1 plus A sub 2 gives you latitude with Polaris. And we talked about the 5 steps for a sight reduction using the Marchesine-Hilaire altitude intercept method. Step 1, determine HO. Step 2, determine GP. Step 3, get your LHA latitude and declination to a whole degree. Step 4, now you could go into Pub 229. You get HC, the D that deals with the extra minutes of declination didn't use, and your ZN. And then finally, step 5, compare HO with HC. Use the memory items CGA, calculated greater away, or homoto, HO more towards, and then pick out your universal plotting sheet and plot it. So that's all there is to it. Again, I'd like to do more videos, one just using the sextant and the other one dealing with just a lot more problems. But at this point, if you're at all interested in, if you have questions or you want me to send you all the copies of all the notes that I have, I'd be happy to do it. Here is my information. I definitely need to come up with a better system. So my email is tnbrill@gmail.com. And I do have a web page under Intrepid YDS, IntrepidYachtDeliveryServices.com. I have a few other items on there, a few other videos and some podcasts. One on offshore passage making, and I could send you those notes too. All the stuff that I wish somebody had told me before I went around the world. And one on crew. Oh my God, that's an interesting one. But send me an email and ask questions. Let me know what your thoughts are. Send me your email, and I'll certainly send you copies of all the information I have. If you are so kind, maybe you can throw a few coins in our bucket using PayPal, or it's actually my flight school address, aerobaticompany.com, or you can find links on my intrepidyds.com. Yeah, whatever funds I can get, I'm going to spend on getting a camera system so I could actually do more of these things and not as ridiculous as this. There we are, the tip jar. I hate doing this, but yeah, I got to come up with a better system. But this is just the basics. If you understand this stuff, the Celestial Nav will be easy to figure out, and in fact, it's a lot of fun. I've done these classes all over the world, in fact, and most people, when they say they're doing this, it's always, oh well, in case the GPS works. Very few people say it's actually fun. And if you're kind of a math geek like I am, this is incredibly fun to do. I call it without being condescending, I call it my pre-Alzheimer's mental conditioning program. It's a hoot. So I would highly recommend, don't be intimidated and go out and have some fun. Play with the stuff. Play with your sextant. Play with the calculations. And you're going to find that it's incredibly accurate. And as I said, just an awful lot of fun to do. Any rate, again, send me an email. Ask questions. Let me know your comments. I'll be happy to send you out my notes. Maybe I'll see you at the high seas, one of the classes. I am doing a few offshore passage making classes. That would be kind of fun. A 12-day class, open only to 2 participants. 5 days on shore, going through everything that possibly could happen when you're offshore. And then we're going to go offshore. And I'm going to throw at you everything that possibly could happen, from climbing the mast to pirates. I love doing all that stuff. But anyway, I appreciate your patience and attention. This has been a fairly long video, and all I can say is hold fast and ask questions and have lots of fun. All right, thank you. Tim out.